For your percentage yield calculations, you need to understand that these calculations are going to be very important, not only for your Organic Chemistry 1 course, but also for your Organic Chemistry 2 course. We will be using these calculations extensively, and you will see these calculations in one version or the other multiple times on your exams and quizzes also. So please make sure that you understand how to solve for percentage yield calculations. Now, so far we have been looking only at the recovery percent. We will now pay attention how to calculate percent yield calculations when two or more than two compounds are reacting to form something new. When we start looking at percentage yield calculations, let us first start at what kind of starting materials you can have. You can have your starting material as a solid, which will be weighed out in grams. You may have a starting material, which is a neat liquid. If you are using a shell vial or some form of apparatus to directly measure it out, you will use grams, and you can also use the density of this particular neat liquid directly in this calculation. And then there is a third kind of a material which is in its solution form. It is not a neat liquid. It is a diluted version and can be reported in molar form. When you take both of these, neat liquid as well as your solution, you can also take them in their milliliter form. When you measure them out, you measure them out in a milliliter form. From your general chemistry, I want you to remember these three formulas that we are going to use to connect all the dots. Moles can be calculated by dividing the weight in grams and the molecular weight of that compound in grams per mole. For solutions whose molarity is known to you and whose volume you convert into liters, you will calculate moles by multiplying the molarity and the volume in liters. A third formula that I want you to remember and memorize is when we calculate mass, we multiply volume and density. Make sure when you're multiplying your density and your volume, you will be left with mass. And at this point, if you don't know how to calculate molecular weight, you need to know that carbon has 12, hydrogen has 1, and oxygen has a 16 mass value or atomic mass value. For each kind of your starting materials, you are required to first convert the starting amount into the moles of that particular compound, for which, depending on what compound you have, if you have a solid, you can directly use this formula. If you have a neat liquid, you will first convert the volume, which is measured, into grams. So you will be given milliliters of your neat liquid. You will multiply it with its density and you will get the moles the mass of that particular compound, using the formula 1, you will get the moles of that particular compound. Similarly, for your solution, you can do the moles of that material by directly using this particular formula. So in all of these cases, you are first required to calculate the moles of the starting material. Once you have the moles of the starting material, you are then required to do the conversion. How many moles of A will be equivalent to how many moles of product? Now, if you pay attention to this balanced chemical equation, what is the stoichiometric coefficient for this particular starting material? 2. And what is the stoichiometric coefficient for your product that has been generating? According to this equation, it is 3. But what is the stoichiometric coefficient right here for starting material B and C? So this is 1 and this is also 1. Using the stoichiometric coefficients, you will then convert the moles of your starting material to the moles of your product by dividing them by the moles of your A according to the balanced chemical equation. This will generate your moles of product, or for our equation, the moles of D. If you have moles, if you have molecular weight, we can calculate the weight or the amount of that substance. So if you have the moles of D, using this particular formula right here, we can calculate the amount of product formed from this particular starting material. And you will do the similar strategy for all the other starting materials. All the starting materials need to have the amount that can be generated from that particular substance. So this is something that you have to remember. Once you have figured out the amounts from all of your starting materials, now you can compare. Comparing all the 3 obtained amounts from all of the 3 different starting materials, we will now have to figure out which is the theoretical maximum amount that this reaction can possibly generate. So we see that out of all of these 3 numbers, this is the lowest number possible, and hence this is going to be our theoretical maximum amount. And the corresponding reagent whose theoretical maximum amount we are going to use will become our limiting reagent. So these are new terminologies that you need to understand. And by the way, why are we actually taking the lowest number to begin with? We can try and understand from this analogy. Let's say that I wanted to make sandwiches and I have these starting materials. I have 2 slices of bread, a leaf of lettuce, and a slice of tomato, and 1 slice of cheese. So these 4 ingredients are our 4 starting materials. From 2 slices of bread, and 1 leaf of lettuce, 1 slice of tomato, and 1 slice of cheese, we can form 1 sandwich. So how many sandwiches would I be able to make from 40 slices of bread, 17 leaves of lettuce, 14 slices of tomato, and 20 slices of cheese? So if you think about it, from 40 slices from this starting material, how much amount or how many sandwiches can I generate? 20. From this particular starting material, I can make 17 sandwiches. From tomato as the starting material, I can make 14 sandwiches. And from 20 slices of cheese, I can make 20 sandwiches. But ideally, what is the number of sandwiches with all of these 4 ingredients together can I make my sandwiches? Which is 14, the lowest number. So I can see that the theoretical maximum yield of the sandwiches that I can obtain is 14. And the corresponding starting material, which in this case is tomato, will become our limiting reagent. If you look at the handout that has been provided to you, there are several practice problems that you can also see. Now, there are a few things that I want to point out here. First, you need to write your dimensional calculations in a horizontal fashion, not the way from top to bottom. Don't do that. So you will need to write each number, each number's unit, and each number's unit and identifier. So what is the identifier? You can label all your starting materials and your products. So I could label it as P, maleic anhydride, it's MANCHD. Or I will write all of this right here. So you need to tell me what is the compound's amount or density that you are talking about. So if you miss writing any of these, the units, the identifiers, or the correct numbers, you will be losing points. At this point, look at the amount. The amount of cyclohexadiene. When you're looking at the starting materials, do not use catalysts or solvents as your starting materials. Only the actual reactive molecules that make something of your product. So for your maleic anhydride, what is the amount that you have? You have this in grams. So you have maleic anhydride in grams, you divide it by its molecular weight. You get the moles of your maleic anhydride. You convert the moles by using the stoichiometric coefficients into the moles of product. And then you multiply the moles of product by the molecular formula of the product to get the amount of product formed from maleic anhydride. You do a similar pattern for your other material, which is in milliliters. Now the milliliters need to be converted into grams first. And then following the above rule, you have grams, you convert the grams of cyclohexadiene into moles of cyclohexadiene using the stoichiometric coefficient, you will convert it into the moles of product and then multiply it with the molecular weight of the product to get the amount of product from cyclohexadiene. Out of these two, who is going to be your limiting reagent? And this is your theoretical maximum value. So CHD or cyclohexadiene is going to be your limiting reagent. Once you have figured out your limiting reagent, and this is done on paper, in the lab, you will actually get some material in your hand that you collect on your vial or on your weighing paper or on your watch glass. This is the actual amount of product that is formed. So dividing actual mass by theoretical max, multiplying it by 100, you will get your percent yield. So these are the steps that you have to follow when you're looking at the percent yield. Always remember this. If you have a neat liquid versus a solution, sometimes to distract you, we will also give you density of that solution. For any solution, you will never use the density. You will always use its molarity. But for a neat liquid, you have to use the density. As soon as you are provided with a concentration, you should understand that you cannot use density. You have to use the molarity.